to get food, then it will try different things, and the things that don't work, it will do less often, and the things that do work, it will do more often. And so it's learning through trial and error. And then the idea of secondary reinforcers, which we're going to come on to in a little bit, but this is the idea of Pavlov's dog, where in the experiment, Pavlov, it's a slightly untrue telling of what really happened, but essentially Pavlov had a dog. When Pavlov gave the dog food, it would salivate, but then he would ring a bell before giving it food, and the dog started to salivate when he rang the bell, even though there's no value with the bell, but the bell becomes a secondary reinforcer to say that, hey, something valuable is about to happen. So the idea of one thing being associated with something valuable, that's an important part of reinforcement learning, as we'll see in a bit. And then more from the side of engineering and computer science, the science of optimal control theory, ideas of dynamic programming, as we'll see later, and value functions. These were all parts of this part of science. And essentially, the question is, can you get some system to have some control within an environment? So it might be that you're trying to get something to slow down just the right rate to say land. So let's say you have an airplane and you want it to land smoothly. Ideas of value functions and dynamic programming can be used there. Now, this isn't quite learning, and we'll see how these two come together, added with some extra elements, and you get reinforcement learning. Okay. So before we get on to what reinforcement learning is, we can see what it can do. And we start off here with an algorithm from Google DeepMind. And this is playing a computer game. It's playing the Atari Breakout game. And I'm not going to tell you how the algorithm is working in the background, but essentially what's happening here is that they've programmed an algorithm which doesn't know the rules, doesn't know anything about how to play this game. All it's able to do is it's able to move this paddle left and right, and it gets some feedback from the environment as to how well it's doing. And it starts off and it plays pretty badly. You see, most of the time it's not able to play the game at all. Okay, but over time, what one finds is that actually it learns that some movements when the ball is in a certain place are associated with it doing well, and so it starts to do those things more. And now it's playing at the level of an expert. And this is after a couple of hours of gameplay. And again, nothing has been programmed in here which says when the ball is coming in this direction, you should move the paddle to the left. Okay, nothing has happened like that. The algorithm has learned that for itself. Okay. After another couple of hours of gameplay, what you actually find is that the agent, the so-called artificial intelligent agent, finds that there's a trick that actually it can send the ball up into the top left of the screen, as you'll see here in a moment, and there's a very, very efficient way to solve the game. It kind of hacks the game by finding this little trick. Okay, so this is just an example. It's just gameplay, just an Atari game where an agent is programmed to learn from trial and error, and it can get to superhuman level in its gameplay. I don't know if anybody has seen the AlphaGo documentary. If you haven't, I highly recommend it. It's on YouTube, and it's about the way this algorithm called AlphaGo by Google DeepMind managed to beat the world Go player. So Go, for those who don't know, is a game a little bit like chess, but is seen as a much, much harder game for computers to learn to play than chess. The state space is far, far larger than it is in chess. And the point here is that if you try to program a computer to play Go by teaching it all of the rules and what it should do in each individual position, it would just be impossible. The size of the state space is absolutely enormous. And so what they did was, oh yeah.
Sorry, John. Can I please stop here?
Please,
so,
yeah.
So this is reinforcement learning, right?
Yes, exactly, yeah. So
So maybe at this point, what exactly would differentiate it from supervised learning with the game and with AlphaGo now?
Great. So within supervised learning, what one might perhaps consider taking a load of games which have been played in the past and labeling those games as to whether they were winning games by one person or losing games by that person, and trying to get a system to find patterns in the data which were able to predict whether or not a game was a losing game or a winning game. So in fact, gameplay is generally quite difficult to think of, even within the language of supervised learning or unsupervised learning. Okay, so gameplay and anything where an agent has to take actions in order to perform some task, really, it makes a lot less sense even within the language of supervised learning or unsupervised learning. It really is simply a reinforcement learning problem. It's a different type of problem. So one can put them into the language of supervised learning or unsupervised learning, but it's kind of unnatural. Does that answer the question at all? Oh, you're muted.
It's clear to me.
Yeah, sorry.
Yep.
That explains it. Thank you very much.
Okay, very good. Okay, so anyway, so this guy Lee Sedol, who's the player here, was the world champion in Go, and nobody thought that it was possible to get a computer to beat somebody at this level. And in fact, what AlphaGo did, what Google DeepMind did, was they essentially got a computer to play itself over and over and over and over again, and learn to find strategies through that gameplay simply through trial and error. And in fact, the remarkable thing that happened here was that not only was it able to beat Lee Sedol in 4 out of the 5 games, you know, very, very comfortably, it found types of play that no human had ever found before. There's a famous move called move 37, I think in game 2 or 3, where the computer played a move and everybody was completely confused. Everybody thought, you know, there must be some bug in the computer. This is a terrible move. And what Lee Sedol realized very quickly was that actually the computer had made a move which no human would ever make, but was brilliant. It was a type of creativity that no human had ever been able to come up with, and opened up an entirely new avenue in the world of playing Go. So, you know, this idea that computers can't be creative is simply untrue. This is kind of a perfect example of a computer learning to be creative and coming up with novel ideas which have value. Okay.
Sorry, Jonathan.
Sure. Yeah.
Please, could I ask you more like a philosophical question?
Sure.
So, do you think you can train a computer to find prime numbers?
Gosh, that's an interesting question. I had a student ask me about this yesterday.
Okay, good.
Yeah, sure. So I think there has been some work done on that. So essentially, what you want to do is, I mean, it's very easy to label a data set with prime numbers, and I think there might have been some work done on that. I don't know what the sort of cutting edge for that is, but yeah, I mean, there you have an extremely well-defined labeled data set, okay, where essentially, you know, your features are the number and the labels are prime or okay, not prime. And so, you know, it's something which is extremely well suited for a supervised learning problem.
Okay.
The question really is there a pattern there to be found? Yeah. And actually the answer is I'm not entirely sure, but it's a great question.
Okay, thanks.
Sure. So this is another example here. So here you have, again, this is a reinforcement learning agent that has learned through trial and error to navigate through environments. So it's a very simple sort of artificial robot. It's got limbs that can move at certain joints, and it's learned through trial and error, through trying one thing and finding it doesn't work, and then trying something else and finding that it does work. It can teach itself to navigate in these environments. Again, if you wanted to program this in, you know, from scratch, this would actually be a very difficult problem to do. You know, there are all sorts of different situations it could get into which you might not think about. Whereas using the tools that I'm going to be explaining about, it's possible to get an agent to learn to do all of this on its own. Okay, I just want to go to one other example here. So this is something called the swing up cart pull, and again, this is a problem that one could program in using the dynamics of the system, the physics of it. But what you see here is something learning in real time. And the aim of this is to try to balance the pole. So you've got a little moving trolley, and to balance the pole on top of the trolley. And what you see here is it's trying different things and it's not doing very well. The first time it was really terrible. The second time, well, it sort of managed to swing the pole up a little more. This time it's going to do something, I think, that looks kind of really crazy. Now it's, you know, this is 5 seconds total experience. doesn't seem to be doing very well, but all the time it's learning something about what does and doesn't work. And the aim here is that it's trying to balance this for as long as possible. It's just going to have another couple of goes here. So trial number 4, 7.5 seconds. So now it's getting some information about what's happening as it moves back and forth in a particular way. Again, no physics has been programmed into the system. And I think in the next couple of iterations, it will basically have solved the problem. Okay, so now you can see that it's doing somewhat better. It's spending more time at the top. And finally, I think it's this one. Okay, so it hasn't quite done it on that one, but on the next one, I promise you it will be able to balance it. Okay, I'm going to move on. Okay, so it turns out that yeah, sure.
Please, let me ask this question. So this brings up a point that is the computer better at learning with fewer trials than humans? So I think the only problem with humans is we don't have infinite time and infinite energy.
Right.
But the computer, so if I were to learn something and the computer were to learn something, would I use less trials than the computer? And
right.
Yeah.
So, I mean, it partly depends on the problem, but I would say in general, the answer is actually that you will be able to learn on far fewer trials. Okay. And the reason for that is that you have some knowledge about the world. So for instance, in that game where you're moving a paddle about and you're trying to bounce it off, you know what movement is. You know that things move in straight lines and that things bounce off things. So you can use that sort of knowledge to your advantage. And that's something called transfer learning. So transfer learning is the idea that you've learned something in other domains and you can transfer that knowledge into the thing that you're doing. So in a sense, one might say that for you to learn that game might take you many years, in the sense that, you spend all of these years building up information about the way the world works from when you were an infant. Computers need to do that from scratch.
Okay. Thanks.
Great question. So one more question at this point. So in this example you just showed, the task is defined for the computer, that it has to balance that, and you have to just give what would be the inputs in this thing, and it has no previous information about the laws of physics at all. So what exactly are you supplying to it?
Perfect. So that's a great question. So the actions that it's allowed to do, so it's allowed to move, so it has a choice at any one time step to move left or to move right by a certain amount. The information it has is the position of the base, the velocity of the base, the angle like this, and the angular velocity. So it has 4 pieces of information at any one time. And based on those 4 pieces of information, it needs to come up with the decision to go left or right. And essentially the idea of reinforcement learning is the agent wants to be given a state, you're here, you're moving in that direction, you're falling down. What is the action that you should take in that given state? Okay? Right. So that's the mapping that it's trying to find.
Awesome. So in principle, it can translate that into a law of physics and give us a light.
So one would have to essentially give something extra. So there are reinforcement learning agents which do try to learn laws of physics, but in and of itself, there's no sort of encoding of the laws of physics within it. It's really a mapping of states to actions. Here is a state, here is the thing that you should do in order to fulfill your task.
So sorry, I meant the algorithm can write down the law of physics that it has learned from this experiment for us. So if we wanted it to.
I mean, you would have to have some extra steps in order to get it to do that. But in principle, one may be able to, yes.
Sure. Great. Thank you very much.
Sure. Okay. So really the sort of philosophy behind this is that teaching all of the fundamental rules, exactly what to do in every state that you find yourself in, this is really hard. It's much simpler to get a computer to learn how to do this itself simply through trial and error. Okay. So one might think that this is to do with supervised learning. Okay. So it does something and then it gets some feedback from the environment as to whether the thing was good or not. But the important point here is that this is the contrast between what's called evaluative learning and instructive learning. Now, in instructive learning, let's say the cart was like this and it fell over and you moved like that, okay? Instructive learning would say, that's not what you should have done. This is what you should have done. And that doesn't happen within reinforcement learning. All that the agent is told is that thing was good or that thing was bad. So its actions are evaluated, but it's not told what the best action to do would be. It has to figure that out. Okay. So the language that we're going to need to use for this is the language of Markov decision processes. Okay. Now what we have here are a set of states, and they're labeled S0, S1, ST1, and ST2. And the reason these are called T1 and T2 is because these are so-called terminating states. Okay. And this might be something to do with the state of the world. It might be to do with the state of the cart pole. And then there are a set of actions that some agent can take. And these are A1, A2, A3, and this A1 and this A1 might be the same thing. So these might be move right, this might be move left, and this might be stay still, for instance. Then what we have are rewards, and we haven't thought about this up to this point, but these numbers here, the -3 and the +5 and the +5, these are rewards. And this is something that has to be programmed in. So for instance, the reward for cart pole might be that any second, any moment that it's within some angle at the top, it gets some positive reward, okay? And maybe any moment that it's down below some angle, it gets some negative reward. And when I say it gets a reward, the computer feeds it a number and says, the state that you are in now is good or is bad, okay? And then we also have what are called transition probabilities. And here, these are the numbers here, the 0.3, 0.5, 0.2. And this says that if I'm in state S0, and I perform action A1, then with probability 0.2, I end up back in state S0. With probability 0.3, I end up in state ST1, et cetera, et cetera. Okay, so this is the structure of a Markov decision process. Okay, it's a set of states, actions, and rewards, and transition probabilities. And this here is the probability of ending up in state S prime, given that you've taken action A in state S. Okay. We need to put another layer on top of this for this to be a decision problem, and this is called the policy. Okay, and the policy is a probability of taking a given action, given that you're in some state. Okay, and you have this, the way that you interact in the world, you'll find yourself in some state, and there'll be some distribution of things that you might do at that time. So, let's say, the alarm goes off in the morning. There's some probability of your action being get up. There's some probability of your action being turn off the alarm. So you have some policy of the way you move through the world. And that's exactly what we need of our artificial intelligence agent to do. It needs to find the best policy in order to increase its chances of getting high rewards over time. So really the policy says, given that I'm in some state, what's the action that you should choose? And the action is generally going to be the probability, the highest, the action which has the highest probability, okay? So we also have to ask, what's our aim? Surely the policy is going to depend on the thing that we're trying to do. We'll come on to that in a moment. So this is the reinforcement learning framework, okay? We've got some agent in an environment, and the agent you can think of as the brain here. And the agent gets some state. So it's told what is the state of the environment that it's in, and it might get some reward from the environment. It takes some action, a time t. The environment changes based on the action that it takes. So it might be move the cart pole to the right, and now there's some new state of the environment. And that new state of the environment is fed back, and a new reward is fed back. And that reward, again, is defined by the person who's writing the program. And the aim of the agent is going to be to change its policy such that over time, its expected future returns, the expected future rewards, are maximized. That's the aim of reinforcement learning. And the trick is, how do you get a computer to update the policy such that it's going to maximize that expected future reward? Okay. So does the world seem like a Markov decision process? Well, within a Markov decision process, one of the important things about the Markov property, of course, is that past states are not important. Only the current state is important. But it seems in the world that past states are often important, that the state that the world is in at the moment, it does actually depend how it got here as to the action that I should take. But in fact, generally one can take a non-Markovian system and can add some sort of memory store which encodes past state information such that you can still consider the system to be Markovian. The world also has lots of hidden information, and in a Markov decision process, you know precisely the state of the system. But there's something called a partially observable Markov decision process, and one can also do reinforcement learning in these sorts of systems. The world is also continuous, so it looked very much in the MDP like, you start in some state, you take an action, and you end up in some other discrete state. But one can actually define continuous state Markov decision processes. Okay. So we need to define the thing that we're going to try to maximize. And what we're going to try to maximize is the total reward over time. Sorry, I don't know why I can't count it. This should say R0 plus R1, etc., plus up to RH, where H is some horizon, some future horizon, which is maybe the end of our trial. Okay, so the reward is received by the agent from the environment. It may be deterministic, maybe stochastic. It doesn't matter too much. And so we got some R, and sorry, this is slightly confusing. The little r here and the big R here, these are really the same thing. So this is just simply the reward from the environment at state 0 plus the reward from the environment at state 1, I should say. And so the total reward over some path through the environment is simply the addition of all of the rewards at every time step. Okay, and tau here is called the trace, which is the path through the set of states in the environment. Okay. So now we go back to Pavlov's dog, and actually what he called it was so-called psychic secretion. And the idea here is that the food can be seen as the reward. So you give the dog food, and that's the reward for the dog. But the point here is that if you ring the bell just before the food, then the dog associates some value with the bell. The bell in itself doesn't have any value in and of itself, but because it's associated with a future reward, the bell has value. Okay, and this is really the important point: is that what we're going to be interested in are the values of states, not necessarily the reward that you get there, but the value associated with the fact that being in this state can lead in the future to getting some reward. So we're going to start off with a very, very simple example. And this is the so-called Gridworld environment. And a Gridworld is basically a very, very simple maze where there's some start state and you can move around here. This state in the middle with the red square with a cross in it is just a state that you can't go into. And one can come up with many different Gridworlds. It's like having lots of different kinds of mazes. This is just one particular example I've written down. And then there are two end states here, given by the green and the reds. And if you arrive at the green state and move off it, then you get +1, you get a reward of +1. And if you get to this one and then move off, you get a reward of -1. And for both of those, the game ends. Okay, so of course, what you want to do is to get here to the +1 state. Okay, and looking at it, it's very obvious how to do that. Well, you could go up here and then across, or you could go here and up and across, fine. But the question is, how do we get a computer to do this without sort of giving it all the information and it having to figure out, a path through some complicated means? We're going to show exactly how to do this using something called dynamic programming. Okay. The first thing that we're going to do, though, is that we're going to introduce something called a discount factor. And this discount factor is this gamma here, and it's a number between 0 and 1. And what this allows you to do is to say that rewards which are far into the future contribute less to the total reward than rewards which are close by. And what this is going to mean is that any agent which is moving through an environment and trying to maximize its expected future returns is going to try to get to high reward states as soon as possible. Otherwise, if you don't have this, then it could move around, for hundreds of years and then finally get to that reward state. And it's not going to be in any hurry to do it. Adding in the discount factor, this number between 0 and 1, is going to make it want to get to those high reward states as quickly as possible. Okay. Okay. So what do we want? We want to find the policy.
Sorry, John.
Yeah, sure.
So by knowing the reward, you mean knowing the sorry, the system has to know the probability of the reward, or
right.
Like,
so what we're talking about at the moment is going to be a system where it knows all of the reward structure.
okay.
Later on, we're going to see actually what sort of the more modern ideas of reinforcement learning, where the agent doesn't need to know anything about reward structure at all. It discovers it through moving through the environment.
Right, because it knows the reward, that's some sort of supervised learning. Right?
Yeah, I mean, it's still not quite supervised learning, because it's only told, the rewards are like a signal to say, yes, this is a good thing or a bad thing. It's not told this is the way that you should get to the reward. So it still has to figure that out for itself.
All right.
Okay. So what do we want? We want to find a policy, and remember the policy is labeled pi, which maximizes the expectation over the discounted rewards given some policy. Okay, so given some policy, and the policy says this is the thing, this is what you will do in this state, either the probability of you doing it, or this is the action you will take in this state. So given some policy which takes you through the environment, there is going to be some expectation value over the discounted rewards added up over time. And the reason there's an expectation value here is because the policy can be probabilistic. So in this state, you have probability of some probability of doing this, some probability of doing that. And secondly, the environment itself may be stochastic, which means that if I perform some action in some state, then some of the time the environment is going to change to this state, and some of the time it's going to change to this state. Okay. So that's why we need the expectation value. Okay.
Sorry, Jonathan.
Sure. Yeah.
Like here, this is some sort of conditional probability, that.
Yeah. So it's conditioned on the policy.
Yeah, but the policy itself doesn't have a probability.
So in a sense, the policy itself can be written as a probability distribution over actions and states. So what is the probability of taking a particular action given that you are in some state?
Sure. Yeah. Okay. This is but this involves the conditional probability itself, in the sense that the expectation value of given the policy is what you are describing.
Yeah, that's right.
But I'm just thinking, just because one usually when one has conditional probabilities given something, then there is also the probability for that something, and then you can integrate over. But not in
so later on, I'll expand this expectation in terms of the actual probabilities, and maybe it will be a little clearer there.
So there is no concept of a likely policy or an unlikely policy.
No, good. No, exactly. That's perfect. Yeah, exactly. So the policy, there is an entire state of policies, and given a policy, there is some expectation value, and you want to maximize the expectation value over all possible policies.
So they are all equally likely in a sense. They have flat.
Yeah, absolutely. Yeah, that's a good point. Okay. So what we can now define is the value of being in a given state, given a particular policy. And the value of being in a given state, given a policy, is the expectation of the future returns. So you could say, what's the value of being in this state? Well, the value of being in this state is dependent on the policy. If the policy is sit here forever, then the value of being in that state is 0. However, if the policy says move right from here, then there's going to be some positive reward associated with it. It's going to be 1, 2, 3 steps down the road, but there's some reward associated with it. So that state there is going to have value given the policy move to the right. Okay, so the value here, and there's a value of every state, and it's dependent on the policy. Okay, and it's simply the expected future returns discounted given the policy. Okay. So now this seems to be a little bit of a problem, because it seems that our policy defines the value. So in order to work out what the value of a state is, well, you need to know what the policy is. But the value of the state will inform what your policy is. You want to find the value of a state you want to choose the policy such that the value of all states is as big as possible. So for instance, if we go back up here, you wouldn't want to choose a policy such that the value of this state is 0. You wouldn't want to choose a policy which is sit here forever. So somehow the value of the states informs the policy and the policy informs the values of the states. So it seems that something funny is going on here. So we can ask the question, what's the value of each state here? And we're going to say, first of all, with no discounting and knowing and the optimum policy. So the policy here is do exactly what you think you should do, move to this state here. Well, the answer is trivial, because if there's no discount, then the value of being in this state is +1, because you know that in the future you're going to get a reward of +1. Okay. What about if you have a discount factor? And let's say there's a discount of 0.9. So now, in fact, there's a subtlety here, because really the reward is obtained when you move off this square. So actually this square has a value of 0.9. This square here has a slightly lower value. It's still valuable, but it's one step away from being in the state here, which is one step away from stepping off and getting your reward of +1. And so here again, this is knowing what the optimum policy is. These are the values of the states. Okay. If we make it stochastic, things get a little bit harder, because if we make it a stochastic system where if I'm in this square here, and if I say I want to move to the right, then with probability 0.7, I will move to the right, but with probability 0.1, I'll move left, I'll move right, and I'll bounce off the wall here. Then we have to be a little bit more careful, because then the value of being in state S22 is 0.9, that's the discount factor, times 0.7, which is the probability of ending up in this state, times the value of being in that state, plus 0.1 times the value of being in that state, 0.1 times the value of being in that state, and 0.1 times the value of being in this state. Okay. So it looks here like if we can define the values like this, well, this just looks like linear algebra. Maybe we can just solve for the values of all states using linear algebra. But remember, this is under a particular policy. And indeed, this is under the policy here we're talking about, where we know exactly what it is that we want to do. But we want the agent to learn this. Okay. So what we'd like to be able to do is to compare the values of states under different policies and choose the policy which optimizes the values of all states. So that is to say, you always want to move, if you're in some state now, and you can move over here or you can move over there, you want to move to the state which has the highest value. Okay? And that's going to be your policy. But of course, the value itself is defined by the policy. So again, it looks like we have a bit of a loop here. Okay. So, as we said before, the value of being in a state, given a policy, is the expectation over the sum of this discounted future returns. Given that we're acting with some policy and we're starting in state S, we can expand this and take out the first term here, the reward of the first step time t equals 0, plus this sum over all future rewards, and we can actually split this up. I've actually missed out an expectation value here, so really this doesn't need to be an expectation value at this point, but the value here is now a sum of a reward and gamma discount times the value of being in the next state. So what that means is, what's the value of being in this state now? Well, it's the value of moving into the state S1. Sorry, it's the reward that you get from moving into the state S1 plus gamma times the value that you already thought state S1 had. Okay. Now we expand out the expectation value in terms of the pi, which is the probability of taking the action A, given that we're in state S, this is the policy, and the fact that the environment might be stochastic. So we take action, we move into state S prime, given that we're in state S, and we take action A. And this is the so-called Bellman equation, which is kind of one of the fundamental equations within the reinforcement learning literature, and says that the value of being in some state given a policy is related to values in next states that we can get to, okay? With the expectation value expanded out, summing over the next possible states and summing over the actions that we might take there, weighted by the policy, okay? The Bellman optimality equation says that the optimal policy, that is the one that is necessarily going to give us the maximum value for any given state, and we label this pi star, is maximizing over the actions. We always want to take the action which maximizes the expected future returns, where again, this is iterative, where here we have the value given an optimum policy in state S, and this is the value given the optimum policy of moving now into state S prime. Okay, this is the Bellman optimality equation.
Sorry, this is the equation that gives the so the optimal policy is the one that gives the maximum value for any state.
Precisely, that's exactly right.
Does it always exist?
So generally, one can look at the local minima. So there may be, for instance, two solutions whereby it's not necessarily unique, but it will always exist in the sense that you will always have some policy which gives you a global maximum. Okay, there may be multiple global maxima. So there may be, for instance, two routes that you can take which give you the same values, but it will always exist. Yeah.
Sorry. So since
Sure.
you mentioned the possibility of two rules, two routes. So I was thinking, why does all this have to be a sum? So for example, it chances upon a route that gives it the same probability, the same reward, or even a better reward than the sum of the previous rewards. Is it going to override that, or is it going to be added to the previous reward?
Can you repeat that? Sorry.
Sorry. So the total reward is the sum of all the previous rewards. So if it's
No, it's the sum of the future rewards.
Oh, sorry. So sum of the future reward. So if it chances upon an alternative route, so let's say it's doing a path integral over two different paths. So one path, it gives an integral because it's been adding the previous rewards and it chances upon something, and another route gives it a better integral in just one attempt. Will it override that, or it will still sum all the possible rewards?
So in this case, there's no chance of sort of accidentally coming across a reward that it didn't know about, because this contains all possible sets of rewards within the environment. What we'll see later, so what we're doing at the moment is called dynamic programming, and later on we'll see that when you're simply exploring an environment, it can be precisely that you come across a reward that you weren't expecting, and that then backdates everything that you thought you knew before.
All right. Okay. So it overrides all the. Okay.
Yeah. Exactly. Yeah. Well, it doesn't necessarily overwrite it, but it updates that information.
All right.
Yeah. Here it's not necessary, because essentially you have access to the complete model of the dynamics.
Sure.
Yeah.
Okay. Good. Thanks.
Sure. So what we're going to do here to find the optimum value is something called value iteration. So we're going to start off assuming that every state has value 0 for all states. And there's a number here. The 0 here is the iteration of this process. So we start off saying that every state has 0 value. The next iteration, we say that the first iteration here is simply using the Bellman optimality equation. Okay, we're again maximizing over A, where here the V0 star, those are all going to be 0. So we don't expect that any states have any value, but there are rewards. Okay. So what that means is that any state which led to a reward would now be seen as valuable. Okay. On the second iteration, any state which leads to a state which leads to a reward will have value. I'll show you an example exactly how this works in a minute, but essentially you can use this iterative procedure to converge, and it will indeed converge. You can prove convergence, that you will indeed converge on the optimum set of values, which defines for you the optimum policy. You can simply get the policy by finding the policy which says that you always move to the state with maximum value. Okay, let's have a look at this. So let's perform this value iteration on Gridworld. Okay, so we start off here and we say, okay, everywhere has value 0. Okay. On the first iteration, V1, this is the maximum over the actions, maximizing really over this here, saying that we'll pick up rewards, and the only place we can pick up rewards are here, where we get a 1 when we step off here, and here we get a -1. So remember, V0 is 0. So the only states that can have any value on the first iteration are ones which are associated with a reward on the next step. Okay, all these V0s are 0. We perform it again, and what we'll see is that now this state here will have value because you can move from there into a state which has value, and it has value from the first iteration. So now on V2, this term here has some value because you can move to this state here, which has value, and this has value because you can move from here onto directly to the reward state. Okay, this one here has minus 0.09 because, well, of course you would want to move up to here, but there's some stochastic probability because remember there's the probability of moving into state S prime given S and A. You're maximizing over A, but you might accidentally fall into here and you pick up the -1, but there's some small probability of that. And there's also the gamma factor here. Okay. In the next iteration, what we see is actually that this one's positive. And the reason it's positive is because now it can move into a state here, which has some higher value. Okay. And what we're going to find is that this propagates back value. And this is simply saying, I'm in some state at the moment, and let's say I'm in a state of getting up in the morning. And getting up in the morning may not feel like it has value, but when I get up in the morning, I'm able to go, get in the car, and getting in the car doesn't have any associated value. But getting in the car takes me to work, and going to work gives me money, and giving me money gets me food, and food, there's the reward. And so what this is essentially doing is stepping back one iteration at a time and saying that actually getting up in the morning does have value precisely because it leads to the state in the future where I get food. Okay. And we can carry on with this, and it iterates back, and eventually doing this enough times, we'll find that this state here converges on the value of 0.26. And now the policy simply says, okay, well, move to the state which has the highest value from any one state. And so the policy is going to be to move to here, to here, to here, to here, to here. Okay. Very good. So the important point here is that we needed to know the model of the environment. We needed to know the transitions in order to perform that value iteration. So if we go back to here, to perform this set of calculations, we need to know the rewards. We need to know all of the rewards. We also need to know the transition probabilities. But of course, you don't always know that in an environment. Okay, you don't always know what the model of the environment is. And sometimes you want to learn simply through trial and error, rather than through this value iteration. Okay. So this is classed as reinforcement learning, but generally one doesn't use a method quite like this. This is simply to show that this idea of values sort of iterating backwards is very important. Okay. I'm not going to go through many details of this, but one thing to bear in mind is that to perform this calculation, if you wanted to solve a game like Tetris, the number of states, well, Tetris has some 10 to the 60 states, okay? So this idea of dynamic programming, where you have to sum up over all possibilities of transitions to all possible states, becomes basically impossible. So one has to find another way of doing this. And one way to do this is a Monte Carlo method, okay? And we're actually going to update our notion of a state value to what's called a state action value. So rather than having V of S, we now have Q associated with a state and an action. And what this says is, what is the value of me being in state SA and taking action, state S, and taking action A? Okay, so now a value is associated with being in a state and taking some action. Okay. And it turns out that you can write a similar sort of Bellman optimality equation for these so-called Q values. So this is the Bellman optimality equation for Q values. And really the difference here is that you're maximizing over your A prime here for your Q values. Okay, very similar. The details of this don't matter too much. So I wouldn't worry if this doesn't make perfect sense at the moment. Okay. So in this case, you would think that here you have 4 times as many Q values because now there's a Q value associated being in the state S10 and moving right. Okay. So what do we want to do here? So for a Monte Carlo method, let's say we start in some particular state S. We want to work out what are the Q values associated with the policy. And I could just write down a random policy, and the random policy simply says, if I'm in this state, I perform this action. If I'm in this state, I perform that action. We're not saying at the moment whether it's good or bad. What we want to know is what is the associated value of that policy. Okay. And so what you can do there is you can start in some states and simply let the policy run itself out. So say I'm in this state, I'm just going to do whatever the policy tells me to do. And if at some point I find some reward, I'm going to send that information back to the very beginning and say, okay, this state action pair has some value because under this policy, I will find a reward. Okay. This state over here, I can run again and again and again, and there'll be some cutoff horizon, and there's no reward associated with it. So I'll say that the state action pair under that policy has value 0. Okay. So what I can do there is I can find the values, state action values, given a particular policy. Having found those state action values, what I'm going to want to do is to say, okay, well, now I have some information about the environment, and I'm going to update my policy. And I'm going to update my policy such that I always take the action which takes me to the next state, which has the highest policy, which has the highest Q value. Okay, so I'm going to basically choose the highest Q value for a given state. Okay, that's going to be my new policy. Now I use that policy and I perform my Monte Carlo rollouts in the environment. And again, I feed back information, and I'm going to iterate through this, updating the policy based on the Q values that I've discovered, then using those Q values that I've discovered, define this new policy, run out the policy, feed back the information, and slowly but surely, this again will actually converge on the optimum policy. So long as every time you update the policy, you do that by finding the Q values which are maximum over some sort of states. Okay. So there are some problems with this, and part of the problem is that if the policy is deterministic, then I'm only ever going to take one path given some particular starting state. Okay, so what one might want to do is to have stochastic policies, which says that some of the time I'll do this, some of the time I'll do this. So you can find, again, the expectation value by performing that rollout multiple times and averaging over that. So some of the time you'll get some reward, some of the time you won't get some reward, and you feed back that information and say, what's the average reward that you get at the end? I know that time is running out here, so I'm gonna wrap up fairly soon. I just want to finish a couple of little things here. So actually, this is exactly what I said. It's called generalized policy iteration. You take some policy, you roll out these this exploration of the environment, starting in lots of different states and figuring out what the Q values are. That gives you the Q values for policy pi 0. You then perform policy improvement that says, I'm now going to define my policy based on the Q values that I found. You then explore using that new policy, et cetera, et cetera. And it turns out that, again, this will converge to the optimum Q values and the optimum policy. Okay. What one can do is use something called an epsilon greedy policy, which says most of the time I'm going to perform the action which is the highest Q value for the set of Q, S, and A's for a given state S, but epsilon of the time, some proportion of the time, I'm just going to take some random action. And that allows you to do some exploration rather than simply exploiting the information that you have. And this is the so-called exploration-exploitation trade-off. Okay. So what we said there, and this will be the last thing, is that I said there that you can do some Monte Carlo rollout of a policy, which says I start my policy and I go all the way out to the end, to some endpoint, and then I feed that information back. Okay. That can take a long time to do. What we can do instead is simply to explore one step ahead. Okay. What we want to do there is to say, how valuable do I think the state that I'm in at the moment is? Okay. I perform the action under the policy, I move to the next state. There's some value associated with being in that state, and I might find that there's some reward that I didn't know was there, and then I'm going to feed that information back and say, hey, actually the next state, well, that was more valuable than you thought, so update the value of the previous state with the new information that actually getting into this next state is actually is valuable. Okay, so this is a so-called temporal difference learning algorithm for reinforcement learning. And what it allows you to do is to take single steps at a time, feedback information, and actually this will also converge to an optimum policy. Okay. I promise you this will be the, no, I'll do one more slide after this, but we start with some arbitrary Q values. So set the Q values all over your state space for all S's and A's, choose some initial state, take some action A, using the policy, using an epsilon greedy policy. So most of the time you'll choose the one which has the highest Q value, but some of the time you'll choose another one. Take that action. The environment will feed back a reward, okay, and some new state S prime. Define a target S prime, which is the reward you found in the next step, plus gamma times the Q value of that next state, and K is simply the iteration number here. Here of the state S prime and A prime being the action you should take under the policy. And now you want to update the previous state weighted with some weighting factor alpha, which is the so-called learning rate, 1 minus alpha times what you thought it was, plus alpha times what you discovered. So it's shifting it towards the thing that you discovered. Okay, you repeat this again and again, and it turns out that this will converge again to giving you an optimum policy. Okay, there's another way of doing that, and this is Q learning, where rather than using the policy to choose the next action, you simply maximize over the next actions in the next states. Okay, so I guess I've probably got through about half the slides here, maybe a little more than that. I'm definitely glad there are questions, and I would much rather get through fewer slides and people understand. So are there any questions at this stage?
Sorry, right for this page. So what does S prime is terminal mean?
Oh, sorry. So the point is that you can step through your space until you get to something which you might consider as the end of the game. So if you're moving through a maze, it might be that you end up at the end of the maze. Okay. So terminal just means that there may be some well-defined terminating state in your Markov decision process.
Boundary condition. Okay.
Yeah, exactly.
Thanks so much.
Yeah. Any other questions? Even if they're sort of from earlier on. I mean, I guess the thing that I should say here is that I think it's important to kind of anthropomorphize a little bit here. So if you were playing a game and you didn't really know anything about what were the good things to do and the bad things to do, you might have some idea about what's good to do. And what you're doing here is you're saying, okay, I think that this thing that I do may be good, may be bad. I perform the action. And if I find in the next state that, wow, actually I get some reward, then I update the information and say, actually, the thing that I did back then, that was pretty good. Okay. And if indeed I've backdated that, then the thing that led to that, well, I can now consider that as being pretty good. Okay, so of course we're having to average over, the stochasticity and the fact that our policy may be probabilistic. But what we're doing is we're updating information all the time based on the rewards as to how valuable the things that we do are. And this very, very basic idea, and I think, even though there are lots of terms here, the idea is pretty basic, is really the fundamental idea that leads to us being able to beat the best players in the world at Go, having robots which can learn complex tasks, all sorts of different domains, self-driving cars, things like this, which the fundamental algorithms are really things like Q learning and policy methods, which I can tell you about another time or offline. But yeah, so this is kind of some of the fundamentals of reinforcement learning. I'm sorry that we haven't got as far as planned, but I hope that has been useful. And yeah, please let me know if there are any questions.
Yes, I have one in the sense that so when it comes to, I mean, of course, this is all very good when you want to do some practical tasks, so winning a game or having a self-driving car. So, but when it comes to physics, so the goal is to learn something, I guess, rather than having a box to learn something. Then
sure.
how do I learn from the box, I guess?
So there are methods of reinforcement learning about finding, for instance, physical laws of some system. And what one has to figure out, so that the key here is defining the reward structure. Okay. So you need to define the reward structure appropriately so that the agent knows what it is, knows what it's trying to get to. So, a very, very simple example, and, this is kind of this is a simple way to think about it. So let's say I've got some experimental data, and the experimental data is simply about what happens when I drop something, and I've got some information about the position of the thing over time. I might have some class of possible models, and let's give it a really simple example where my parameter G is some unknown parameter. What you might get a reinforcement learning system to do is to update parameters in a particular way such that the output of its own model matches as well as possible the true data. Okay, so you would have to create a class of models, and then within that sort of state space of models, so long as it can move around that state space of models, and you have an appropriate reward function, which is how close is the output of that model to the real world, you can move closer and closer towards coming up with a physical model. However, this has been done in certain examples. They're using reinforcement learning and using sort of supervised learning methods. That's not necessarily to say that this is the best way to go when one wants to actually have some real understanding of the dynamics of the working of the universe. But these tools we're sort of developing over time, and it may be that from these we can learn eventually to come up with novel models. Any other questions?
More questions? Maybe not from here. Looks like in the audience, in the online audience. Well, hope trade is still alive. Okay, so this is very interesting. Thank you very much.
Yeah, so John, if you, I see you've written it in Key. Maybe you can send us a PDF of the
for sure
of the talk.
Yep.
That would be great, so we can share with the students. That's mostly
absolutely
one of the follow-ups we get after every seminar.
Sure. Yep.
And yeah, so maybe just I can just tell the students that you're involved in this project Mathemafrica, I guess.
Mm-hmm. Yes.
You want to say a few words about it? And
Thank you very much. Yeah, so Mathemafrica is a website. It's mathemafrica.org. Is a website that I started 6, 7, maybe 8 years ago with a group of other people. And the idea is that it's a blogging platform for anybody within Africa who wants to write about mathematics. It's generally at university level, starting from undergraduate, going up to sort of research level. But the idea is it's a multi-blogger, multilingual platform for anybody within Africa who wants to blog about mathematics. So for instance, I put all of my lecture notes for my first year pure maths course on there, and then they're accessible to everybody. So if anybody likes the idea of blogging or would like to make their course notes open access and would like to write blog posts about their course, or enjoys writing blog posts about research that you've read about or talks that you've gone to, let me know. I guess Shrai, you can send people my email address if they want it, and I can set you up with a blogging account, and you can just get blogging. But it's got lots of material there for anybody who's teaching first year maths, also lots of research material, sort of research level blogs, along with book reviews, things like that. So yeah, if anybody would like to get involved, that would be fantastic. I'd really appreciate that. Yeah.
All right. Okay.
Right, then I guess that if you don't have more questions, then we can thank you. It was really very interesting talk. And yeah, some questions come up, we will channel them to you.
Sure. Wonderful. Many thanks, everyone. Cheers.
Thank you.
Thanks very much, John.
Bye, everybody. Thanks.
Wonderful
Bye.
talk. Thanks.
Bye for now.
Bye.